All right, are we ready to switch back to reliability? Well, one, thank you guys for joining us. I am going to actually start and give a presentation on our new Immersion Reliability Committee. A little bit about how we're structuring it, a little bit about what we're doing, what we've done so far, and where we're going with this. So, one of the things I want you guys to recall is how many here were at Global in Lisbon? If you were at Global and you were attending, you would recognize this. And this was presented by Rich, who you saw earlier if you were here with the committee in our community outreach. But Rich presented this slide when he was working with gaps for immersion warranty implementation. And one of the big gaps that was identified is we have no standardized immersion reliability test methodologies, which makes it very difficult to make warranty risk assessments because you have no reliability data to actually aggregate to provide the risk assessment to your business unit that is making that business decision to provide a warranty. So this was identified as one of the major implementation gaps for immersion to proliferate across the industry. So what we did with the Reliability Committee is motivated by actually trying to close this gap. So right now, data centers, we all know, want data that validates the reliability of their immersion solution. And historically, what's been done is data centers that are pursuing a POC, they take a server, convert it to the necessary conversions to make it immersion compatible, and they just dunk it. And that has been more or less successful depending on the POC. It's almost random, it seems. So when a potential customer has a bad experience with a random server that they dunked, one, it's very expensive to put a server and then just have it fail. And two, it destroys the confidence in the capability of this technology to be reliable. So what we needed to do was set up some more structured testing methodology so that we can improve the success rate of deploying an immersion solution, because data centers want warranty support to support their hardware investments, and that requires thermochemical risk assessments from reliability engineers such as myself to provide to our business units so that they can make that business decision on whether or not that is supportable. So what is our scope? So our scope as the Reliability Committee is both thermochemical quality and thermochemical reliability. And I'm going to actually define those terms for those of you that are just introduced on what is thermochemical reliability. So thermochemical quality, this is what we're used to. This is the material incompatibilities that can impact the performance of components and their supporting materials when the systems are immersed in fluid. So essentially, these are the things that we are essentially testing for now. Do we have a fundamental material incompatibility? And I call it a fundamental thermal quality issue because if you have an incompatibility that shows up with material compatibility testing, it's kind of a showstopper. You're definitely not going to be reliable. So we can screen out a lot of things that just aren't going to work by doing a simple material compatibility test. But then we have a second component to this, and this is the part where the industry is still very much learning what the additional impact is. And what I call this is thermochemical reliability. And this is the degradation of components and systems because of specific chemical reactions between the fluid that's contaminated by the tank and system materials during the service lifetime. And that contamination that is dispersed in the fluid then has secondary reactions with other components in the system. I will say most of the failures that I've seen at the system level are not necessarily, we screen out the fundamental material incompatibilities. Most of the failures during a service lifetime are most of the time related to these types of effects where you have contamination in the fluid that then has a secondary effect downstream and creates a secondary chemical reaction with something else in the system. And there are so many materials in these systems, and frankly, we don't have material compatibility on all of them, and that's one of the gaps we're trying to close. So how are we doing that? How is this work? How is this Reliability Committee structured? Well, notice that I structured this as a pyramid because there is a necessity for actually doing this testing in very much an incremental approach where there's foundational material compatibility. Do you have foundational material compatibility of a single uniform metal, ceramic, polymer, or composite material? And this has actually been addressed very adequately in the current fluid and materials compatibility guidance that has been published by OCP and that the material compatibility workstream is inheriting and will be providing an update to soon because we do know that that white paper does need a revision. We are then layering on top of that component compatibility. This is now where you start integrating multiple bulk materials into a functional component. So those components have a functionality, they have a workload, they have a performance aspect to the fact that they have multiple bulk materials. So then we have to have an additional layer of compatibility testing for both the performance of those functional components and the fact that they have multiple materials, which are often not currently in basic bulk guidance, compatibility guidance, to assess, are those components functional? And a great example of this is gap pads and TIM2s. If you take a NIC card or you take a PCIe card and you inherit a TIM or a gap pad material, I think we've all seen where sometimes those are and are not compatible. And that's a characteristic sort of fundamental issue with the system that's trying to reuse parts that have been qualified for air, is sometimes they just aren't compatible. But we can evolve that and change that with some more guidance and testing. We then layer component reliability on top, and this is where the probability of a component will fail due to interactions between the fluid and the service lifetime. And when you talk about server, a server is many components that have been aggregated into a server. So server is at the very top, because then we have to approach that as sort of a system level test. But in order to start with server reliability, you have to have the rest of the pyramid fairly well understood in order to make this cost effective and expedient. So one of the first things we did back in end of July, early August, is we had a community outreach, where I called in the community and said, okay, I want to hear from you on where you would like to see this new reliability committee address the gaps in thermochemical reliability within the community. What are your pain points? So we did a mirror board collaboration. We had the community put their feedback out there. I then summarized this feedback, and I used this feedback to actually develop our deeper dive questions for the roundtable sessions we're having tomorrow. So this is a call out for anybody that is really interested in this topic. We are going to actually continue this discussion with a deeper dive question on what topics and what problems do you want us to solve. So the reliability focus areas that were generated from this feedback include some of the things that we would also kind of recommend, expanding some of the recommended materials list to include characteristic and recommended server IT equipment, things like cables, TIM2 materials, but some of the more ubiquitous and standard materials that are in servers, and improve the test procedures and success criteria guidance. In component compatibility, component reliability, server reliability, everybody was like, how do I do this testing? Completely agree with you on that one. We have a lot of work to do on that. But in addition, is like, okay, this fluid contamination question, what kind of contamination? Where is it coming from? What are thermochemical failure modes, right? What do they look like? Well, how do I have some education of what should I be looking for, right? And then what actually is the impact of the fluid contamination on server reliability? So then I generated, with the team's effort, with my workstream leads, we generated this additional layer of questions. And these are some of the questions, and I put this out here because for anybody in the rally, I want you guys thinking about this, because I want you to come and give me some of the answers. Now, this is just a sample. The sky's the limit, but this is the type of depth that we really want to discuss at a community to really focus on what are the true technical problems that this community needs us to solve and how best to solve them within the community. And notice I say, what are the technical constraints to execute component reliability testing? Notice I said technical constraints, because trust me, we all know that there are schedule and cost constraints. But when I focus specifically on technical is, if you're a fluid supplier versus a component supplier, what are your capabilities to do testing? Because it doesn't do the community good if we develop testing procedures that nobody can actually execute. So we do need to understand what is the community capable of and how do we tailor that testing guidance for the resources you have to execute that testing. Now, something else we have in progress. We have a white paper in progress through the material compatibility of server components, and this is a critical first step. And I think I alluded to it in some of the earlier questions, is how do we test the material compatibility of components? These, again, are components that have a functionality to them. They have integrated bulk materials. So I want to actually say, I have many of the team that has contributed to the paper. Please stand up and be recognized. This has been an incredible team, very active team. I want to see at least the 5 my stakeholders that have been contributing to this white paper stand up if you're in this room. And I want you to wave your hand and say, be recognized for the fact that we have done a ton of work to get this far. So this team is the foundation of our component compatibility team. And we've been working on this for about 5 months now. just to come up with a framework of how do we, as a community, address material compatibility of components with all of the complexity of the different components within the work stream. Because it's not as simple as just one component. We have to have something flexible enough that can do everything from a connector to a CPU to a GPU to even a coin cell, right? So we want to build something that any component vendor can use, and that requires us to really broaden and have that community support. So what we've outlined is a procedure where we have a 4-step testing process, including SOAK. And what we're looking at here is not only looking at the functionality of the component during that compatibility testing, but we're also starting to add on the additional layer of what contamination is that component contributing to the immersion fluid, and how is that potentially impacting the reliability of the immersion fluid in addition to the reliability of the component. So the 4 steps are baseline testing. 1, does this component even meet your T0 criteria before I soak it? So basically your control, right? You soak it, and again, some of that, we will have different recommendations for different soaking for different fluid types. We then do a physical inspection. Again, this will, trust me, your physical inspection is kind of your first pass. Did your TIM2 material disintegrate? Did you see a discoloration? Do you see cloudy fluid? And this is a great test to say, what are my subsequent testing? So we also confirmed that the fluid meets the minimum fluid requirements for a critical subset of fluid properties, because yes, if you have the wrong contaminants in the fluid, it can actually impact critical fluid properties as well. Then we energize the component. Does it turn on? And we want to do that as a safety test, like does it turn on? And believe it or not, that could sometimes be harder than you think if you got a short that you can't see, or you had a critical electrochemical interaction that you didn't see. But I mean, that's the first step. And this is where we maybe start looking at, based on some of the initial tests, do we have any organic contaminants in the fluid? And then we go into phase 4, which is, okay, it turns on. It turned on safely. It turned on as I expected. Now, does it still perform as I expected? So this is where you, again, based on the level of component, you do the performance workload. And this is, again, where some of the feedback that Dennis gave is, coming into some of the industry standards, how do you measure success? What kind of performance workloads? What kind of safety standards do these components have to meet after this test? That's definitely going to be part of that feedback process. And again, we're going to look at if you have some additional fluid characterization that critically impacts the performance of your system, we're going to want to do some additional testing on that. So this is an outline of a white paper that's currently in progress, and we expect that it'll be published next year. It is a very dense paper. There has been an incredible amount of contributions and discussion for something that is this new to the community, and I am just beyond excited on how it's shaping up. As far as the leadership team, Rolf did introduce them earlier in the day, but I want to give another shout out to say our material compatibility team, again, led by Puneeth and Stephen, they do have a call schedule for 3rd Tuesday, 8 to 9 a.m. Pacific Standard Time. Component compatibility, Bo. I'm in there as an interim lead because I'm still kind of coordinating the white paper as we speak, but I'm an interim lead. The co-lead, of course, is still open for that as I transition back to server reliability. And the meeting schedule for that is 1st Tuesday, 8 to 9. Component reliability, Dennis, who you heard from, and Emre, one of my colleagues at Intel, is running component reliability. And server reliability would be led by Betsy and myself. Expect that a couple of these, material compatibility, component compatibility, are ongoing efforts. Component reliability and server reliability will start kicking off towards the end of this year. So expect to see some meetings from the Workstream leads come up November-ish, December-ish. We're going to start looking at those mailing lists. So please, if you want to get involved, join those mailing lists and start from the ground up. This is a fantastic chance for you to really contribute and have a voice in where we're going with this new committee. So my call to action, participate in the Thermochemical Reliability Roundtable event on Sunday. So those seed questions plus anything else that you guys want to contribute to say, what are the problems? As my component in the ecosystem, what problems do you need us to help you solve to produce immersion solutions that you have confident meet your reliability requirements? Join the Reliability Workstream email distribution list for meeting invites and updates. Attend the meetings, and please just contribute. Contribute anywhere that you want to contribute. We've got a lot of efforts going on, and we need your help. Any questions? Oh, come on. It has to be questions. Even if it's general thermochemical reliability questions, it's something that most people haven't even heard of.
Okay, so hi, Sam. So with thermochemical reactions, the activation energy is very dependent on the temperature. Did you find, the amount of testing that I can see that you've done and the scope of this work is phenomenal, but there's other operational variables that might amplify certain effects, and there's complexities with the interactions once the principal reactions have happened, but they're also, I think, dependent on the operating conditions in the tank, right? So is that another factor that we need to consider in this?
Yes and yes. I think that the way that we do it and the way that we have approached this, and you'll see the presentation. Here's a seed question for the thermochemical reliability presentation that I'll do after lunch. But I will be presenting the approach that Intel's taken to actually do reliability testing on Ice Lake CPU and PAL 6. So I will be presenting some of that as the holistic approach of how we've approached it. Back to your question, there's a little bit of both. So as far as the activation energies, you can't create a new activation energy because every new equipment and fluid combination is a new chemical reaction. And so it would be very inefficient, incredibly inefficient to create activation energies for accelerated life testing for every single combination out there. So that makes we have to think about things a little bit differently. And as far as the electrochemical, that's why we have to do testing at both the component level. So when I said component reliability, that's when you're going to go more towards the understanding what the actual reliability of a component as far as their use case lifetime is. But then when you do server reliability, when you start aggregating things at that level of integration, you have to approach the reliability a little bit differently. And you start doing more of what we call system level reliability statistics, where it's more of a reliability demonstration test. And that's also where you can get some of the electrochemical failure modes. And while you still have to do server level work, because a full component level in a clean fluid isn't going to capture all of your risks when you start integrating things at a system level. And that's why it's incredibly critical that you have both a component, because as a server integrator, and I'm going to point to Austin here, he's going to say, I have to integrate all of these components into a server. How do I know which components I'm picking to put into a server are reliable? So how do I make the best shot of success of creating a solution that would be reliable? And that requires all the component vendors to come in and say, okay, let me have, very similar to what we do. Like if you're a component vendor, you produce a qual plan, you say, my component is qualified in air to do this performance metric, this is the testing I've done, and here's my MTTF and MTBF fit rate, right? We have to create an additional layer of that for the specific fluids that we know our fluids are component in. We're going to just have an additional sheet to say, okay, here's our component, here's the test data, here's the fluid that it's compatible in based off of industry standards that have been aligned, right? It's just going to be another layer on our tech data sheets that we provide to ODM vendors to say which components do they integrate when they're building servers. That's where we need to get to.
So the reliability testing, so part of reliability is something that you estimate beforehand, and then this is the second part of it, which is actually testing the reliability. Mm-hmm. So there are equations that you come up with, or we have, where you come and estimate the reliability of a product in immersion. It's hard to do, I agree, but that's the first step. And current reliability, as you clearly mentioned, there are a lot of steps that go into it. There's a component which is non-operational, operational, mm-hmm. but we don't know exactly when it's going to basically end of life, or something happens to the component in the fluid. Mm-hmm. What I want to know is, what would you suggest for accelerated testing? So,
okay, so that's actually a good one. So you can actually accelerate reliable testing. So while the chemical reactions are not a degradation due to heat, you can still use the Arrhenius relationship to accelerate the chemical reactions. Now the trick is you can't actually correlate that very easily to an actual equivalent use case lifetime because of the lack of activation energies and the inability to get activation energy for everything. So what we've done, and what I'm kind of recommending, is that you use your thermomechanical baseline. And this is kind of what I'll present, is we started to say, hey, I have an activation energy. I have a very good understanding of what my use case lifetime is for my thermomechanical baseline for my degradation. Now, any heat I add or any degradation I see on top of my thermomechanical baseline would be a contribution from thermomechanical. So we've expedited this a little bit by having what we're going to control, using our thermomechanical baseline as a control. And basically looking at the difference between the degradation rate in our thermomechanical baseline against our thermochemical baseline from equivalent test temperature conditions in the fluid, and then said, is there a statistical difference between the two? And any difference would be the thermochemical contributions. So this is where we're actually trying to expedite some of the things, like try to leverage the data we've already collected and use the data we have collected to add this on, but do it in a way that's very efficient.
As a follow-up to just what you mentioned, like, would you assume?
I'm getting kicked off the stage,
Yeah. There you
but
go.
come find me afterwards. I'll definitely answer your question.